Our last speaker for today is Andrei Jaikin, who will tell us about detecting key products and key factors in profinite.
Thank you very much. Thank you very much, organizer, the workshop and the program invitation. So today I will talk about a joint work with Enrique Sousa and Pavel Zaleski. So the motivation comes from the problem of ремесленников. So he asked whether is a finitely generated free group profinitely rigid. So, okay, recall the profinitely rigid means that if we have a finitely generated residually finite group, so this is always my assumption, and we have another finitely generated residually finite group, then such that we have isomorphism of finite completions, then it means that the group gamma is isomorphic to the group gamma. So the most important result in the area is about problem of ремесленников is a result of Wilton. So Wilton proved this for groups which are fundamental groups or free groups of a cycle. So if gamma is so graph the fundamental group of finite graph with the vertices free and edges cyclic. Also, gamma is hyperbolic. Then gamma is isomorphic to profinite completion of free group, implies that gamma is free. So later, Morales shows that hyperbolic you can change by residually finite. This was done by Morales. So this is what we know about ремесленников problem, and today I will not give new result about ремесленников.
Morally proof that if gamma is residually finite, or you mean under the assumption?
So under the assumption of residually finite. So Wilton showed it for.
I don't understand.
Yeah. So Wilton showed that if you have a fundamental group of a finite graph with finitely generated free vector subgroups
And hyperbolic. That's what we.
and hyperbolic.
Ah.
Yeah. And,
I thought that it's two different results.
yeah. Then, but hyperbolicity you can change by more natural condition in this situation, which is residually finite. Yeah. So today I will not present new results on ремесленников problem. So as in Holger talk, cannot prove main problem, so we generalize it and try to learn something from this. So the condition, so the two properties that I want to consider today is property to detecting of free factors and free products. So let's see a class of group So we will say that profinite completions detects free products in C if for all group gamma, for all finitely generated residually finite group gamma belonging to C, if we have such that gamma hat is non-trivial, so this is my way to denote profinite free product, so it's a non-trivial profinite free product. Then we have that gamma is non-trivial free product. And similarly, we can define the notion that profinite completion detects free factors if any residually finite generated gamma in phi and any subgroup H, finitely generated subgroup H in gamma, such that gamma hat is free profinite product of, in this case, the closure. This is the closure by H in gamma hat. Then we obtain that so these are, of course, related notions, but they are somehow independent. And they have appeared recently into works, and in the case of virtually free groups. So for virtually free groups, if C is the class of virtually free groups, so it was proved by De Bessa, Porto, Zaleski. They prove 24. So they proved that in this class of virtually free groups, profinite completion detect free factors, and in the paper of Alejandro Garrido and myself, we proved that the second property for virtually free group, then if the profinite completion in the class of virtually free group detect free factors. And for today, I will.
Can I ask one question, Andrei?
Yeah, of course.
So this, you mustn't be the intersection of K with gamma.
What?
You mustn't be the intersection of K with gamma.
Not. Of course, it's yeah. This is it's an interesting observation. Of course, if you have in general, if you have gamma is L K in general, you cannot expect. It cannot expect something like this. Okay. This approach, of course, does not work. Just think about a free profinite group. It has a lot of free profinite group has a lot of factorization of free profinite product, which does not come from factorization of free. Yeah, so U, it's some subgroup which nothing to do with A.
Is there any way to deduce the first result from the second one, or?
No, they are not related. Okay, you can use the same technique, but one does not follow from one. So today, this is C is the class of the fundamental groups. Fundamental groups of graph, where GV is virtually free. So vertex subgroups are virtually free. And the H subgroups virtually free are virtually cyclic. So this is the class where we know Remesnikov, solution of the Remesnikov.
And the graph is fine?
Okay, of course, because you can assume also is finite because I consider it only finite generated group, so you can change the graph and make it fine. Yeah, so okay, for this class we know quite a lot, and for example, we know where this class is. So if gamma is a finitely generated, residue finite group from C. So we know that gamma is hyperbolic exactly when gamma does not contain Baum-Slach-Solitar subgroups. So this is a result of Bistvina-Fegin. We know that gamma is residually finite. If and only if gamma does not contain Baum-Slach-Solitar groups NM with NM, the model of N, M, and 1 all be different. Okay. And so this is a recent result of Amgral Monroe. This is a paper in archive from 2024. And also we know that when gamma is north, so it's gamma does not contain. Baum-Slach-Solitar and M with difference. This is result of twice. So all these three conditions.
Yes. Hi, Kerim. Andrei, I'm a bit confused.
Yeah.
What you see now, if gamma is, what is C now? Gamma is left if and only if it does not contain.
Baum-Slach-Solitar.
What do you assume about gamma?
Gamma is a finitely generated residual finite group from C. And C is today is a class of the fundamental groups of virtually free groups with virtually free with virtually cyclic edges. Okay, so to recall, just in case, lerf, so gamma is lerf, means that for any finitely generated subgroup of gamma, so if we consider intersection of the closure of H in a profinite completion with gamma is, you can separate finitely generated subgroups in profinite completion. Okay, so the main result that I want to present is the following theorem. So let gamma be finitely generated lerf group in C. So if the profinite completion of gamma is composed non-trivially as a profinite free profinite product, then we have the same, okay, we have a decomposition as a product of the discrete group gamma. So my plan for today is explain okay, the proof of this theorem, then explain why we cannot prove it when assuming residually finiteness, and explain what we know in the case of residually finite groups, and then also discuss what we know about detecting free factors. Yeah, we know much less. Yeah.
Say gamma is residually finite, and then you have a condition for residually finite.
Yeah, here it's residually finite. Here.
And then above, but you assume that gamma is finitely generated residually finite. Those are two separate.
No, so yeah.
Okay.
Yeah. So gracias. Yeah, thank you. This is. We don't assume residual finiteness. Yeah. So, what tools do we have to attack this the theorem? So we have mainly three tools. So the first tool is Wilton's result. But I will formulate it in a different way. So Wilton's result says the following. I will use it in the following. Let gamma be a finitely generated hyperbolic group from C. If gamma hat is projective, so I need it more than to be free, then gamma is virtually free, is virtually projective. So gamma is virtually. So projective, it's projective means in profinite word means that it's a subgroup of the free profile. You can define it in different ways as profinite group of cohomological dimension 1, or for example, a subgroup. So this is the first tool. with our result with Alejandro. So, okay, it says the following. So if we have a group residually finite group from C, and F is a virtually free subgroup of gamma, then every finitely generated FP gamma submodule of this completed group algebra of gamma, F submodule of gamma hat, can be then for every finitely generated FP submodule of gamma, call it M, there exists a free FP submodule such that you have the following containments. So what I am saying exactly here, so we start with a group gamma, and we consider this completed group algebra. Now we consider a finitely generated virtually free subgroup, and we look at this completed group algebra as a FPF model. And as FPF model, so FPF model, this object is a union. It's a union of free FP gamma, FPF. So we proved it when F is gamma, but it's easy to see that you can extend it for any subgroup gamma containing F. So for example, it implies that is flat. So is flat as FPF. So this is a very strong condition with a lot of consequences. So this is the second tool, and the third tool is the classical results about derivations. So these results appeared in the work of Stallings, but
So the M prime is really an FP gamma module, not just an FP.
sorry.
So it's really M prime is really an FP gamma module, not just an FPF.
Yeah, it's FP gamma model, of course, but I see it as FPF model. So I would like to have this conclusion as FP gamma model. I will discuss it later. But I just have this conclusion for subgroups of gamma which are virtually free. So, and the third tool, installing many people. This is from the book of Dixon. I think it's this version, maybe it's due to Dunwoody alone. So the results that I will use is the following. Assume we have a derivation of gamma in a projective free FP model. Then there exists a gamma 3 x, so 3 on which gamma acts, such that with finite H stabilizer, and such that H subgroup H fix a vertex if and only if the restriction of this derivation on H is in. So let me recall. So derivation by derivation, so it's a function from the group to gamma model. So we have satisfying the following conditions. And so this is C1, so the set of derivations. Then in a derivation, so we have to take some element M from M and can define dm is minus 1. You can check that it satisfies this condition. So it's B1. This is a set of inner derivations. And okay, the first homology group is this quotient. So, of course, this theorem, it's interesting only for non-inner derivations. So, for example, if we take inner derivation, so the tree here is just a point. Not very. But once you have a non-inner derivation, so once you have that this group is not trivial, you can really construct nice actions on tree, and all, in particular have a decomposition of the group gamma with as the fundamental group of graphs with finite pitch.
What are the assumptions on gamma here?
No assumptions. Okay, maybe you need finitely generated just like this. Yeah. So, I will think about this case. Yeah, so, okay, we have these three results. I will now explain you the proof. But first, I want to explain it in the case of virtually free groups. So this is what we did with Alejandro, more or less. And you will see the difficulties which occur in the more general case and other difficulties. So let's assume that gamma is virtually free, for example, for a model. Okay, so we start with non-trivial decomposition of profinite completion, and this gives us a derivation. So how do we construct this derivation? So this decomposition implies that augmentation ideal of the completed group algebra will be decomposed as direct sum I don't explain the notation, but I think you understand what it means. So we can decompose the augmentation ideal as this direct sum, and now we can write any element from augmentation ideal. We can write it as element from here and here. And so now we can define the derivation. Sending the element G, sending to its L part G minus. Yeah.
The superscript G is not just like the G sub.
Sorry?
The superscript G is not just like the G sub module generated.
This?
Yeah.
Yes. It's yeah. So this is augmentation ideal of FP. This complete. So it's if you in discrete case you know it's probably, but the same works in profinite case. So once you have free decomposition, you have decomposition of the augmentation ideals. So it means that we constructed a derivation. We constructed a derivation with coefficients with this very big model, gamma model, and it's not in it. It's not. It's not difficult to see that it cannot be. Now gamma is finitely generated, so it means that the image of the derivation is finitely generated model. Submodel of PG. And so we can use this. So we can use. So yeah, we can use it. Belongs to now M, which is free. So now we can define, it means that we can define derivation D from gamma to M that's applying the same, doing the same things that we did before, but now we look, the image, we look at not here, but in this smaller submodel. And now we have this with Dix-Dunwoody technique, yeah, and we can obtain that gamma acts on some tree with finite edge stabilizers. Okay, it's not okay. With our derivation, it's really have very particular form, and so with a bit more work, we can change. We can prove that gamma acts on another tree, so we trivial. And this gives us decomposition. So this is more or less the proof. Okay, now assume I want to do the same, but for our class C. So if I want to do it for the class C, then of course I have 3, which I said it's about all groups, but what we don't have is 2. So this is would be very interesting to understand whether this property of virtually free groups can be extended to more general setting. So this is, I believe, is my next question. Find other examples. Okay, yeah, maybe I will ask it for surface group. Is it true? Yeah, there are other examples of groups with this property that really we want large groups. Is it true that if gamma is a surface group, then, okay, let's ask, for example, then FP gamma hat is a union of free FP gamma submodels. This is maybe too hard. Yeah, I don't know. You can ask smaller. This model is flat. I don't know. So, as you see, this property 2 we only know for virtually free groups, and so we cannot repeat the same proof. So we need to change. So now we assume that gamma is the fundamental group of the graph of group. I assume gamma is finite. GV is virtually free, finitely generated virtually free. And G is virtually cyclic. So in order to be able to use this argument with Alejandra, so what we have to do, we have to do some reduction. And so the reduction is the following. We say H in G in Y is elliptic, if the H group subgroup corresponding to is infinite, and is contained in some conjugate of so I start with the same condition. So I have that gamma hat is decomposed as K, free profinite product of K and L, and I define H elliptic if its corresponding subgroup, it's contained in a conjugate of L or conjugate. And so we have another graph. So this is a graph which obtained by collapsing all non-elliptic edges. The graph obtained from Y collapsing all non-elliptic. So this graph, the vertex of this graph is what is this? Is a connected component of gamma without non-elliptic, without elliptic. When we remove all elliptic edges, so the connected component will be vertices of this new graph. And so in particular, so we can write gamma is like P, so this new graph, this new graph of groups, and G tilde B is isomorphic to P X G where X is a connected component of Y without elliptic. And now what we know about this group? What we know about this group? So first, because we assume LERF, this is where LERF appears. So we obtain that the closure of this group in profinite completion of gamma is isomorphic to its profinite completion. Second, we can prove that the closure is projective, and also we can prove that no Baumann's solitary subgroups are this. Now applying the result of Wilton, we obtain that this group is virtually free. Okay. So it means that we can work not with graph gamma, but with graph gamma tilde, which have this additional assumption that all H subgroups belongs to a conjugate of L or conjugate of K. This is
Daniel, do you expect conjugates of L to intersect G at all?
yes, yes. This is basically what we prove here. So if it doesn't intersect, yeah, for example, yeah, if you start with this situation, for example, there are no elliptic edges. Basically, you will have only one component. So it will mean that we can prove that in this case, this group is virtually free. So, okay. And so you are in a situation when the group is virtually free and you can do what I explained. So this is the situation. Yes, it can happen. Okay, so now we can assume that all edges are elliptic. And okay, for simplicity, this is really not very big assumption. I will assume that there is only one edge. So all edges. One are elliptic. And so there is only one vertex. Sorry. Okay, basically I can do it. So if I have two different, several vertices, I can add more edges. So if I start with group gamma, so then I can collapse. I can collapse all vertices in one big edge, one big vertex, and so will give me, instead of group gamma, this will appear group gamma F2. So basically, this change, it's passed from gamma to gamma F2. Of course, for this group, we have non-trivial decomposition, but the decomposition that we construct really has to do something with initial decomposition. So it will be not this one. But okay, but this helped me explain how. So I assume that there is only one edge, one vertex, and now the idea is, as in the proof of a virtually free case, so we start with this is now this more general situation. One vertex. V. So we in this situation, so we start with the decomposition. We have this element dA. We have this element dA. And now what I will consider is the restriction of dL on my vertex subgroup. So this gives me an element. Here, which is nomine element. Okay, yeah, you just in situation here. If there are edges, it's not in the element. And now I use the same observation as before. I can embed the image of DL on GV in some free FP G, I call it GV subnet. So, and again, what I used here, so our result was 100. And now, new derivations that I will construct is the following. So I now. So what we know about this derivation. So we have that it is contained in. We know that VV is free. So the action of the derivation on elements of GV is as the action of derivation which comes from this decomposition. And also we know that V is inner on any on H subgroups. So from this we construct another model. This is already a model for gamma. Just extend the S-covers. And we use Meyer-Ditoris for this model M. So we have this exact sequence. Sum for all ages. So we have an element dv here, which we can, the image, we can somehow think about it like dv. Now, this element, the condition that it's inner on all H subgroups, say us that it goes to 0. And the Myers-Ditoris say us that here we have a lifting. We have some D, which comes, which sends to dV. And because dV was not inner, this one is not inner, and this gave us a derivation which can be used to construct the composition of gamma, first as a fundamental group of graph with finite edges subgroups, and then with more work as construct another action on another tree with subgroups. So I'm short of time, so yeah, maybe I will mention another result. So in the case of, so yeah, as I said, I really would like to prove this for residually finite because it's natural condition. But okay, there are a lot of difficulties. And for example, first one, when we use here, when we use really here, we, in order to use Wilton theorem, we needed Lerf. So if we would have Wilton theorem for virtually compact special groups, we can probably do this tape, but at this moment we don't have such a theorem. But okay, but also we can ask, if we just assume finitely generated, what we can say about profinite completion of gamma. So in this case, yes, we have a result. So in some sense, which give us a hope that we can prove the same theorem but with finitely residually finite condition. So a result is the following. So let gamma be finitely generated residually finite group in C. Then gamma is homologically so it means that really gamma hat, so it can be think like gamma hat knows a lot about gamma. So many properties of gamma you can really read from. I will stop here.
Any questions?
Actually, I have one comment and one question. First comment. I think one need to add that this result actually proves that with the class C, one-endedness is a profinite property. Because if you take a group from class C and you take abstract free product such that the profinite completion is the same, then profinite completion automatically splits as a free product, free profinite product, and so therefore we can.
But okay, with the Lerf assumption.
Yeah, I mean, with the assumptions of what you have here. Understand? But my question about your result with Alejandro in the free group, when you have this setting for L and K, right? I think, right? Can you deduce from the setting that actually the second factor is free profile, or it is just projected?
No, we don't. Yeah, such thing is very difficult. So, yeah, okay, it's related with this question.
Yeah.
So, the question.
Well, it depends on the order K or L, but I mean.
So start with a profinite completion of
For free, right.
finitely generated free group.
Yeah.
Is it possible to compose it as free profinite product with KL, one of them at least, not profinite?
Yeah,
not
but
free profile.
Here, no, I asked this question because in that setting that we started with, K actually intersects the original free group. So it comes from the free factor, this K. So I asked whether it gives implication to the second factor. So if
no, okay, so
yeah, so my assumption is the following: that suppose we have the original group, free group, and subgroup, right? Finitely generated subgroup, such that in the completion it gives free factor K. Can we then deduce?
I'm not sure I can do it in free group.
Then there will be some other
Yeah, there are.
L dash, which will be free. Which will be
Yeah.
profinite completion of the.
One will come from.
Yeah, but I mean, the other thing is, you have here free factor, but I mean, whether this one is free, this is my question, not another one.
No, see, okay. I will.
Any other questions?
So, is it known that the number of ends in genuine is not a profinite invariant, or that's?
No.
Number of ends,
Number of ends.
it is more stronger than Remesnikov question.
No, okay, for some groups maybe it's not. So I don't know any example.
You expect it to be true or false?
Ask Martin to construct all non-profinite properties. This will be one non-profinite.
you say more how you prove this G hat? No, so this G tilde has a projective completion. I guess it is related to your choice of Y.
Yeah, so yeah, it's because edges does not intersect with L and K, so, and this really gives you some a lot of restriction on possible intersections.
This is Profinite has set.
Yeah, basically it's Profinite. Yeah, it's easy to see in discrete case, it's automatic, but in Profinite it's more or less the same.
Any other questions? Let's thank Andrew.